that. There's a pulsar. Oh, so these objects that are flashing light, we call them pulsars. So here's a pulsar in the center of a globular cluster. So there it is there when it's bright, aimed at us, and here when it's not so bright. Now, how do we detect the neutrinos? So we've put together this great theory of how high mass stars collapse and generate neutron stars, but is there evidence to really support it? And the most direct evidence that really confirmed that this was right was the actual detection of the burst of neutrinos given birth to by the nearest supernova to have gone off, as far as we know, in the last 400 years. It was in a galaxy about 3 Milky Way diameters away from us called the Large Magellanic Cloud. And we had a neutrino detector at the bottom of the Homestake gold mine operating. And let's see, was it that one or was it, I think it was the water detector actually, in Canada. And it detected the neutrinos which ran into some of the electrons inside the water in that Sudbury detector and caused those electrons to accelerate up to near the speed of light and emit a bow shock of light. Characteristic Cherenkov radiation, little circle of light, and the circle of light tells you where they came from, and where they come from. They came at the time and from the direction of that supernova, which was detected that very night. So that's Cherenkov radiation, something I'm not really going to ask you to understand, but basically it's when you take a charged particle and you accelerate it up to past the speed of light in that medium. Now, you might think, wait a minute, Rick, nothing can go faster than light. Nothing can go faster than light in a vacuum, yes. But you can go faster than the speed of light in that medium. And then you emit a shock wave, a bow shock. And that kind of light is called Cherenkov radiation. I'm going to skip that. So there's supernova 1987A. This was the star that blew up in the Large Magellanic Cloud. And we saw the neutrinos. We detected the neutrinos from that explosion. They arrived hours before the light did, but then that too made perfect sense. The photons, after all, had to spend a few extra hours fighting their way out of the hot ionized cloud that was the surrounding star that they were blowing up. And so they had delayed a little while before they were finally freed and then could travel, of course, at the speed of light to get to us. The neutrinos have a tiny bit of mass, and they actually travel slower than the speed of light. Very, 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 very slightly. But because they didn't have to work their way out through that layer of surrounding star because they are only feeling the weak force, they actually got a head start and beat the light to us by a few hours. So there's the neutrino observatory at the bottom of the Sudbury mine, and these are all these little dots, these little things on top here are the other ends of photomultiplier tubes that are really aimed inwards inside this giant globe of water. It is giant. See this person here? That's a person. Give you some scale. There's another person. And it proved that indeed neutrinos are emitted, and therefore a neutron star is born at the centers of the stars. Let's look at the cosmic abundance of the elements. Well, we talked about this, how gold is created. More nuclear physics than you need to know. Forget about that. Our process, a little bit too much detail. This should be a purple slide. But I did want to show this. I think it's pretty interesting. Hydrogen and helium are very common. But then these are the two elements that emerged from the Big Bang, as we'll learn later. Lithium, beryllium, and boron, extremely rare. They're like as rare as gold and silver. You might not think so, And you might say, well, gee, you know, lithium's not that valuable. Heck, I throw out lithium-ion batteries all the time. Yeah, well, it's because the Earth is, because lithium is so lightweight, it tends to collect at the surface of the Earth, and salt processes concentrate it further into dry lake beds. And so nature has managed to take this cosmically very rare element and concentrate it for us so that it's pretty easy to find. And so, yeah, it's not all that valuable. Same with beryllium and boron. Okay, and then much more common again, carbon, oxygen, neon, nitrogen. These are elements that are made early in the sequence, so lower mass, more common stars, but still medium mass stars and high mass stars will make these, and they'll be in the outer envelopes of these onion stars, and they'll tend to get blown out. So yeah, there's a lot of those. But then these elements are much more rare, and then, whoa, this turns around. What's this hump doing here, centered on iron? Well, it's because when a star develops an iron core, it blows up. And a lot of that iron, now we talked about some of the iron making a neutron star in the center, but a lot of that iron just gets blown out. And isotopes of that iron can turn into nearby elements, so manganese and nickel, for example, cobalt. And then these elements are much rarer, so these are only created in our process, the rapid process of the supernova explosion itself, or in neutron star collisions, which, of course, are very rare. Gold, silver, platinum, uranium, etc. Another picture, same thing. And then I mentioned cosmic rays. So what these are bits of supernova explosions. They get accelerated by processes in the magnetic field of the galaxy. They're already moving very fast, many tens of thousands of kilometers a second from the supernova itself, but then they can get accelerated further by bouncing around in the magnetic field of the galaxy, so that when they finally arrive at us, they could be essentially moving at the speed of light. And they bang into the upper atmosphere, and they have so much energy they create all kinds of unstable baryons like pions and kaons and lambdas and all kinds of stuff, some of which make it to the ground. I'm going to skip that since we are getting an hour and 10 minutes into our lecture. We only have an hour 30. So these are the possible end states of a star, depending on the mass. If your mass is less than 1.4 solar masses, then you can be stable as a white dwarf. If your remnant mass is more than 1.4, then you can't be a white dwarf, and you could be stable up to 2 solar masses as a neutron star. You can find neutron stars that are less massive than 1.4, but then that's because they were created in stars that were much more massive than that, and then blew up, and a lot of the outer layers got knocked away. And then the theoretical limit is 2 solar masses. So if you go beyond 2 solar masses, there's nothing that can hold you up. You bend space around yourself so severely that the radius of curvature of space itself is sharper than is the radius of curvature of your surface. And you essentially collapse in on yourself. There are no pathways out from that. You become a black hole. So for a black hole, the gravitational redshift would be 100%. All the energy of the photon is eaten up in its attempt to escape. In other words, none of it gets out. So if you had a very strong black hole very, very nearby, and you had it in a rich star field, then it might distort the star field like this. So what you're seeing is that the black hole's in the middle here, and no light gets to you from that direction because that would have to be light from inside the event horizon, and it can't get out. the light that you see concentrated along the boundary is really the light of background stars that are back, actually, they are back here behind the black hole. And that light was heading off in this direction, and then when it passed near the black hole, it got bent by the curvature of space from the intense gravity, and it got bent into your line of sight, so that now you see the concentrated starlight of really all the stars that are inside here now put onto the surface, okay, of the two-dimensional star field that was back here is now concentrated into a one-dimensional field called the event horizon of the black hole. One way to talk about the event horizon is the escape velocity at that point is the speed of light, or was right at the speed of light, and inside it's greater than the speed of light, and so nothing can get out. I'm not sure why this diagram is here. I'm going to skip it. Now, it was in one of my Astro 4 classes. I know we already showed this cartoon. If it was our day class and not our night class, I apologize for going over this again, but then this will be good because now we have it recorded. I'll even try to post this on YouTube, and so this maybe will be useful. Anyway, cartoon dating back to the 2008 recession. There'll probably be also funny ones about the current recession, the coronavirus recession that we're starting right now. Okay. So, let's look at how stars evolve in a star cluster going forwards in time. So what happens is the high mass stars that are up here will evolve through their whole lifetime very quickly, as we talked about. So these guys are already evolving off the main sequence, even though this star cluster is still very young. The highest mass stars might only last for a few million years on the main sequence. These stars are all main sequence stars. They're burning hydrogen into helium in their core. But then what about these guys? Well, these guys are so low mass, they're little red dwarfs, that they haven't even gotten down to the stability point and become main sequence burning stars. They're still they're poking along, slowly pulling themselves together under their weak gravity, and they aren't yet really fully stars. They're in the variable star stage called the T-Tauri stage of evolution. So now this is pretty cool. We can age date a star cluster. That's something you cannot do with an individual star sitting out there all by itself. Stars kind of age like we all would like to do. We'd like to come of age, be full flower, be beautiful for our entire lives, and then not age at all on our surface until the very end, and then we just, we die and that's that. That's what stars do. They go through most of their life looking, fresh and lovely until just the last 10% of their age, and then they go through big changes. Then they pay for it all. Okay, so how do we age date a star cluster? Well, we understand stellar evolution, we believe, very well. We can, in a computer, age date a star and find when it runs out of hydrogen in the core, and that's when it will now evolve off the main sequence and go up and become a red giant. So it is this main sequence turnoff point. That's what tells you the age of a cluster. So for this very young cluster up here, NGC 2362, it's only 10 million years old. The turnoff point is way up here at a luminosity of almost 1 million times the luminosity of the sun. The Pleiades, bright naked eye cluster, it's about 60 million years old. M11 that we looked at the beginning of this show is about 150 million years old. The Hyades are almost 700 million years old, and M67 is 3 billion years old. Most open clusters, when they get to be that old, have already completely dissolved, but M67 is a particularly dense cluster, and it's actually still hanging around. Okay, so that's our stellar evolution talk. The next lecture that we will have will be on end states. We'll talk about black holes in a little more detail, and then begin to talk about the Milky Way galaxy. So we don't yet have any quizzes. So again, I'm making this during still the beginning points of turning this into an online course, something I've never done before. Generating and giving fair quizzes in an online format is not so easy, and I haven't really had time to flesh it out yet. So I will tell you by email when we're ready for our next quiz. Okay, gang. I will see you next time then.